Ralph the Wonder Gazelle begins from rest at the top of a 10-meter tall playground slide. The coefficient of friction between Ralph and the slide is 0.2. How fast will he be going at the bottom of the slide? We will begin this solution by drawing our LOL diagram. So our system is Ralph the Wonder Gazelle, Ralph, and the Earth. So at the top of the ramp, Ralph is not moving. So initial kinetic energy is 0, but he has gravitational potential energy, UG initial. And at the end, he is moving, so he's got some kinetic energy, K final, and he has no gravitational potential energy at the end. And there's friction in this problem. So you know that friction is going to take energy out of the system. That's why I made this thing is larger than this. So friction is taking energy out of the system. So the work of friction, I'll show this. This is a work of friction. This work, non-conservative. So this thing minus this equals this. So the problem here is we have to find out the force of friction. We need to calculate the friction. So that's the hardest part of this problem. So first of all, let's draw a pictorial representation. So here's the hill. This is theta, which is 30 degrees. And Ralph is on the hill. Okay, there's Ralph on the hill. Let's look at the forces acting on Ralph. We got force of gravity, straight down. This is the normal force. And then there's a force of friction. And that is kinetic friction because he's sliding down the slide. So we need to find the force of friction. Do you remember what the force of friction is? Force of friction kinetic equals mu k times Fn. So we need to find the normal force first. So let's draw a free body diagram. And remember, when we have a ramp, we tilt the axes of the free body diagram. So let's draw it like this. So this is X, this is Y. Now we put on the forces. We have force of gravity, which is m times g. This angle in here is theta. Then we have the normal force, perpendicular to the slide. And then there's a force of friction. So we need to find the normal force. Here's how you find the normal force. You need to apply Newton's second law of motion in the y direction. So let's do that. Sum of forces in the y direction. We got Fn going up. Then going down is a component of gravity along the y-axis, which is mg cos theta. So minus mg cos theta. This thing is not accelerating in the y direction. So acceleration is 0, so the right side here is 0. Then we solve this equation for Fn, and we get Fn equals mg cos theta. So then put this into our expression for force of friction. And we get force of friction equals mu k mg cos theta. So now we need to find the work done by friction. So we have the force. So let's find out how far he traveled. So this is h. It equals 10 meters. And when he slides down the ramp, how far did he travel? Let's say he traveled this distance. Let's call this S. So we find out what S is from trigonometry. Sine theta equals opposite over hypotenuse, which is 10 over S. So S equals 10 over sine theta is 30 degrees. So it's sine 30 degrees. Sine 30 degrees is 1/2. So this is going to be 10 over 1/2, which is 20. So 20 meters. So S is 20 meters. So what's the work done? So the work non-conservative is force of friction, kinetic, times S times cosine 180 degrees. Why is it 180 degrees? Because displacement delta x is down the ramp, the force of friction is up the ramp. So 180 degrees between those two angles. So we're going to have here, so this is negative, this is -1. So it's just going to be negative. Put in the force of friction. UK mg s cos theta. So that's the work non-conservative. That's probably the hardest part of the problem. Everything we learned about in our dynamics unit we had to use here. So now let's write down the energy equation. Energy initial plus work non-conservative equals energy final. K initial plus UG initial plus work non-conservative equals K final plus UG final. So now let's put in what we have for each of these things. K initial is just 0. So 0 plus UG initial is MGH. He's at a height of H, so plus MGH. By the way, the mass of Ralph is M, and we don't even know what M is. So we just call it M. Let's put in work non-conservative. It's this. So minus mu K MGS cos theta equals K final 1/2 MB squared. UG final is 0. So that's what we have. We're trying to find V. We don't know M, but it doesn't matter. It cancels out. It's in every term. M cancels. Now I think to proceed, let's get rid of this 2. So multiply every term by 2. 2. 2. 2. So these cancel. So what do we get? We get V squared equals 2GH minus 2 mu K GS cos theta. And then we should take the square root of both sides. Take the square root. Square root of V squared is V. So we get V equals square root 2GH minus 2 mu K GS cos theta. Like that. Then we put in our numbers. square root 2 times 9.8 times 10 minus 2 times 0.2 times 9.8 times 20 cos 30 degrees. You work this whole thing out, you get 13.8 meters per second. So that's our answer. What, are there any questions? There's a question, can you explain what S is? So S is just the distance he traveled down the ramp. That's his displacement along the ramp. Shouldn't there be another cos theta after mg for force of kinetic friction? Another cos for force of kinetic friction. Oh, you mean here? I don't think so. I think we just have one cos theta here. It came from this. It's a component of the mg along the y-axis. So it came from here. Fn is mg cos theta. So we don't have another cos theta here. There is a cos 180 degrees here to take into account that delta x and force of friction are in opposite directions. Can I take a picture? Yes, you can take a picture. Why is WNC negative? It's negative because of this, because of the cos 180 degrees. Displacement and the force are in opposite directions. So that means you're going to have a cos 180 degrees. And cos 180 is -1. So when displacement and force are in opposite directions, the work is negative. If they're in the same direction, the work is positive. So 180 degrees came from Ralph sliding on a straight line. Yes, because he's going this way, he's going that way down, and the force is up. Oh, how do we get the work non-conservative? That is a complicated one, isn't it? First of all, we need the force of friction. Force of friction is mu k Fn. So we have to get Fn. So we draw our free body diagram. Sum of forces in the y direction. It's Fn minus mg cos theta equals 0. So we get Fn. It's mg cos theta. So put it here. So force of friction is mu k mg cos theta. And so once we got the force of friction, the work is a force of friction times the displacement times cos 180 degrees, because they're in opposite directions. The S, displacement, comes from this triangle. Sine theta is opposite over hypotenuse. Opposite is 10. The hypotenuse is the displacement S. So 10 over S. So S is 10 over sine 30. And sine 30 is 1/2. So 10 over 1/2 is 20 meters. Okay. Okay, I think that's it. I think everyone, is that all the questions? I well, see, there's two thetas in this problem. There is this theta, 30 degrees to the ramp, and then there's the theta between force of friction and delta x. So that theta is 180 degrees. So I've taken care of that here. This is a cos 180. This theta is 30 degrees. So it's two different thetas in this problem. So the second cos theta in your question is cos 180 degrees. Why do we multiply by displacement? Because work is force times displacement. So force of friction times the displacement times the cosine of the angle between them. Okay, so that's the problem.